Hello everybody and welcome to section 1.1. In this section we are going to investigate the question, how do we measure velocity? And to help us find the answer to this question or to investigate this question, we're going to look at an example. In example 1, we are going to look at an example where we have an object that's fired into the air with an upward velocity of 100 feet per second. And its height in feet after t seconds is given by the function f of t equal to 100t minus 16t squared. Okay, so what's the situation? Well, we have an object. It's being tossed or fired up into the air. And so let's draw what this looks like. I'm going to draw that over here to the right of the graph. So we have some object. Right here we have the ground. And our object, let's say it's a ball. It starts on the ground and then it's being fired into the air, so it's moving up. At some point, it's going to hit the highest point it's going to reach, and then it's going to come back down. So actually, I'm going to change colors. So then it's going straight back down until it hits the ground again. So it's just going up and coming back down. We can visualize the height of this object with our graph. So over here we have a graph that has time on the horizontal axis and then it has height on the vertical axis. And you see the same idea that I drew over here on the right. As time goes on, so time is moving this way, our object is gaining in height. At some point, it reaches its highest height right here, and then it's coming back down. It's losing height again. And we don't see the whole story. We are stopping after 4 seconds. But if we continued with time on the horizontal axis, if we kept going, we would hit the ground again eventually. Now, we would like to know, how fast is this object moving? How fast is it moving up and then moving back down again? So what we are asking for is the velocity, the upward velocity of this object. We know the initial velocity, it's given as 100 feet per second, but you can imagine initially this object is moving up very, very, very fast, but then because gravity is pulling it down, it's slowing down and eventually turning around and eventually hitting the ground again. We would like to learn more about what is happening to the velocity of this object during those 4 seconds that we can see here on our graph. To get us started, we're going to find the average vertical velocity of the object. So average velocity is something that we have seen before. So this is a tool that we can use to learn just about how fast that object is moving in general. So we're going to find the average velocity of the object on the time interval from 1 to 4 seconds and from 1 to 3 seconds. So first let's look at the time interval from 1 to 4 seconds. I can write that here using interval notation. 1 less or equal to t less or equal to 4. So I can write it like that. It means the same thing as our interval that starts at 1 and ends at 4. We want to find the average velocity on this time interval. And from the work that we've done before, the average velocity right here is the change in height over the change in time. How much did the ball gain in height during the time interval that we're investigating? So in our case, how did the height change during the 3 seconds between 1 and 4 seconds that we are observing our object? Now the change in height, we can find that using the formula for our height function. We don't have a scale on the graph, so really we can't get the change in height from the graph. We really have to use our formula. And we have learned before that the change in height is the function at our ending time, so f of 4 minus the function value at our starting time, f of 1. That is the change in the height during those 3 seconds. And then we are dividing by how long this time interval is, and I already said it's 3 seconds, but just to see where that's coming from, let's write down 4 minus 1, because that is where the 3 seconds came from. All right, so we can evaluate our function. We have a formula for our function, and we can evaluate that formula at 4 and at 1 second. So at 4 seconds, we get 100 times 4 minus 16 times 4 squared. I'm going to underline again. Right here is the formula for our function. And that is f of 4. And then we are subtracting f of 1, which is 100 times 1 minus 16 times 1 squared. And all of that is divided by 4 minus 1, which is 3. The square brackets that I put in, one purpose for the first one is just grouping them together, but for the second brackets right here, this one and this one, I really needed to put those in there because I'm subtracting the entire expression, and I want to make sure that I'm subtracting both pieces. So I need these brackets, or you could use parentheses, whichever you like better. Okay, so let's evaluate what this is. If you just punch those numbers into your calculator, you will see that this is 144 for f of 4, and then minus 84 for f of 1. All of that divided by 3. And if we evaluate this, we get 20 feet per second. For our average velocity, we should pay attention to what the units are. And since the height is measured in feet, let me put that on our graph. So the height is measured in feet and time is measured in seconds, then our average velocity has units of feet per second. So our ball right here between 1 and 4 seconds travels at an average velocity of 20 feet per second. So that was the first task we had. Now let's look at the second one. So on the second time interval, we are starting at 1 second as well and stop at 3 seconds. So a shorter time interval. Let's see what happens there. The computation is very similar. The only change is the length of our time interval and the ending point of our time interval. But we are still computing the change in height over the change in time. And now we are computing f of 3 minus f of 1 divided by 3 minus 1. Very similar calculation. For f of 3, I have 100 times 3 minus 16 times 3 squared. And then I'm going to write it down again. F of 1 was 100 times 1 minus 16 times 1 squared. All of this is divided by 2. And when you plug this into the calculator and you multiply everything out, you have 156 minus 84 divided by 2. Oops, that's a very strange looking 2. I'm going to fix that. Which computes to be 36 feet per second. So we computed two average velocities, once between 1 and 4 seconds, one between 1 and 3 seconds. Let's look at the graph to also see what this means in terms of our graph so that we can visualize what's going on. So for both examples, we were interested in a time interval starting at 1 second. And then for our first example, we looked at, okay, what about between 1 and 4 seconds? So we also looked at this point right here. We computed the average rate of change, the average velocity, and graphically we computed the change in height between those 2 points on the graph divided by the change in distance, time distance. So we computed the change in height over the change in time. So this 20 feet per second number really is the slope of this line. So the slope is 20 feet per second, and it gives us the average velocity of our object between 1 and 4 seconds. We can also visualize the second average velocity we computed between 1 and 3 seconds. So there we looked at 1 and 3. So we are looking at another point, and that seems to be the highest point that our ball reaches. And so we computed also the slope of the steeper line. And indeed, it looks steeper and it has a higher value. It's 36 feet per second. So the slopes of these lines, we called them secant lines before, so the slopes of these two secant lines are our average velocities. So for the first one, it was 20 feet per second. For the second one, it was 36 feet per second. And we can see that the size of those two numbers really matches the slopes that we can see in our graph.